In this module, module 22, I'm going to give more examples of finite state machines. So we'll talk about 3 examples: a washing machine controller, a sequence detector, and a door code detector. So in each of these, we're going to follow the same procedure, which is the FSM design procedure that we talked about last time. So, for example, suppose we have a washing machine controller. So we want to control what that washing machine does. Let's suppose we have our inputs. So we'll do the first step where we draw the inputs. We always have clock and reset and clock here. And now let's suppose we have some additional inputs. We have a start input and a pause input. And maybe we also have a mode input. And we have an output that says done. Maybe we have a done output. It's like a buzzer that goes ding, done. Okay, so we've started with our black box diagram showing just the inputs and the output. And so now let's draw our state transition diagram. We'll start in some reset state, S0. Always have our reset input showing what state we go to upon reset. So S0, we're waiting for a mode input. So if mode is equal to, let's say we have 2 modes, just wash and idle. So if the mode is 0, let's say for the mode, 0 is idle and 1 is wash. So once maybe it's a lever that we click, and once we go to the mode equals 1 state, so it's now into the wanting to do, to run a load of washing, we go into the S1 state, and it's waiting for the start signal. So as long as it's not, start hasn't been pushed, maybe it's a button, and it stays there. As soon as start is pushed, it goes into state 2, the washing state, and continues in that state until it indicates that it's done. So maybe we have a signal from the washer. Maybe it detects movement or some kind of signal that says not finished. And once it's finished, then it goes into state 3. And at that point, maybe it asserts the done signal, like connected to a buzzer, waiting for the washer to be activated again. So we can add this finish input that indicates when the washing cycle has been finished. And we go back here and say, okay, well, we also had a pause. So if it's in the washing mode, state 2, and pause gets pressed, then it goes into the wait state. And maybe we have another output that stops the washer. So maybe we have a stop output. So we can add that output here. We wait for the start button to be pressed again. As long as start is 0, it stays in that state. It goes back when start is pressed again. So we need to modify this, but it's the start of our state transition diagram. This is a little bit more complex than what we had in the last module. But pretty good. A couple things to note. This output stop is asserted in that state. In any state where it's not listed, it's 0. Same thing with done. So done is 1 in this state, but any state where it's not listed, that output is 0. Okay, so we have a little bit of a problem here in that all of the cases, or they're conflicting cases. So this arrow here shows that when finish is 1, if you're in state 2, you should go to state 3. But what happens if finish is 1 and pause is 1? We have conflicting information. If you're in S2 and you get pause is 1 and finish is 1, then which state is it? The wait state or state 3? The wait state, we can number that S4, the wait state. Okay, so this is a problem. So we can, basically to fix it, we need to get rid of that conflict. For this one, we could say pause and not finish. And this one can be not finish and not pause. So now we can check it. So we have these inputs. I'll just put F and P for finish and pause just to make it, I can write up here F equals finish, P equals pause. And so let's see what combinations we have covered. If we have all of them, all the possible cases covered and only once. So if finish and pause are both 0, it'll take this transition. All right, that one's taken care of. That's the only transition it would take. If finish is 0 and pause is 1, it's going to take this transition. If finish is 1, independent of pause, it will take this transition. Okay, so we've covered all the possible cases for finish and pause, and we've covered them only once. Okay, so now we can write our state transition table. Current state on the left, and our inputs. And we put our next state on the right. So if our current state is S0 and our inputs, well, in this case we're only looking at mode. If mode is, right up here I'll say what these are equal to. So M equals mode, just to make it easier to write. ST equals start. F equals finish. P equals pause. So if we're in S0, mode is 0, then our next state should be S0 again. So here's this transition. If current state is S0 and mode is 1, the next state should be S1. This transition. If now we're in S1, so again, once we're in a given state and we're writing this our state transition table, don't worry about S0, S4, S2, and S3. Just worry about S1. So if we're in S1 and start is 0, then we want to go back to S1. If we're in S1 and start is 1, then we want to go to S2. If we're in S2, and now we have a few more variables here, but finish is 0 and pause is 0, then we want to go back to S2. If we're in S2, finish is 0, but pause is 1, then we want to go to S4. If we're in S2 and finish is true, everything else is a don't care, then we want to go to S3. If we're in S3, well, this one's easy. We don't care about any of the inputs. We just want to go back to S0. If we're in S4, and what's this one depend on? Start. So start is 0, wants to go back to S4. If we're in S4 and start is 1, goes to S2. Okay, so now we've covered all of the transitions in our state transition diagram. And now we need to encode our states. So here we have 5 states. So the minimum number of bits we can use to encode 5 states is, well, I can't use 2 anymore because that would only encode for 4 unique states. So I have to use 3 bits. So let's go ahead and write our state encoding. So we have, again, 5 states, S0, S1, S2, S3, and S4. And we have to use now 3 state bits. Remember, S sub 2 is not equal to big S2. Big S2 is state S2. S sub 1 is not equal to big S1, and S0. S sub 0 is not equal to big S0. Okay, so we'll just use binary encoding. State S0 will encode as 0, state S1 will encode as 1, state S2 will encode as 2, state S3 will encode as 3, and state S4 will encode as 4. Okay, so now we'll encode our state transition table. We have our current state and our inputs, and then we have our next state. So current state, we have S2 to S0. Inputs, we have M, start, F, finish, and P. And our next state is S2 colon 0 prime. So we start with the top line. S0 is encoded as 0, 0, 0. M is 0. Everything else is don't care. Next state should be 0. Next line, state 0. M is 1. Everything else is a don't care. You should go to S1. Next line, we have S1. ST is 0. Everything else is don't care. You should go back to S1. If the current state is S1 and ST is 1, everything else is a don't care. You should go to state 2. Next line here. If we're in state 2, so 0, 1, 0, F is low and P is low, everything else is don't care. Next state should be S2. If we're in next line, S2, F is low and P is high, everything else is a don't care. We should go to state 4. If we're in state 2 and F is high, doesn't matter what anything else is, then we should go to S3. Now the next line. If we're in state 3, doesn't matter what any of the inputs are, the next state should be state 0. Next line. If we're in state 4 and ST is low, everything else is a don't care, all the other inputs are don't cares, then we should go to, or stay in state 4. If we're in S4 and ST is 1, doesn't matter what the other inputs are, we should go to state 2. So now we've written our washing machine state transition table, the encoded state transition table, and now we can just read it as sum of products off of the table. So here we get S2 prime, the equation for that. S2 prime is equal to, well, S2 bar and S1 and S0 bar and F bar and P, or this next one is going to be S2 and S1 bar and S0 bar and ST bar. Now we're going to write our next state equation for the next state bit. S1 prime, well, now we have ones in 4 conditions. So S1 prime is going to be S2 bar, S1 bar, S0 and ST, or S2 bar, S1, S0 bar, and F bar and P bar, or S2 bar, S1, S0 bar, and F, or the final case, S2, S1 bar, S0 bar, and ST. Finally, our last state bit, we have 3 possible cases of 1s. S0 prime is going to be S2 bar, S1 bar, S0 bar, and M, or S2 bar, S1 bar, S0, and ST bar, or S2 bar, S1, S0 bar, and F. So here we have our next state equations, and we can write our output table as well. We have our current state on the left, our outputs on the right. Our outputs are done and stop. Our current state bits 2 to 0. So we're going to get 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. So done should be true only in state 3, S3. And stop should be true in state 4. Okay, so if you put this into a K-map, you'd end up getting, let's go ahead and do that. And this is for the done output. 0, 0, 0, 1, 0. And so what do we put in those empty boxes? We don't have the encoding, we don't have states for 1, 0, 1, 1, 1, 0, and 1, 1, 1. So we put don't cares in that. There's no way we can get to those states, so they're never going to happen. So we put don't cares there just to help us, if it will help us minimize our equations. And so we look at the done signal, and we can see that, oh, okay, well, we can circle those two. And we end up with done equals S1 and S0. Without using the don't care, we would have gotten done equals S2 bar, S1, S0. But using don't cares, we can minimize that a little bit more. We get done equals S1 and S0. So now we can do the same thing for stop. I mean, you can almost see too from this is that whenever S2 is 1, stop is going to be 1. Because there's no other used state where S2 is 1. We'll also see this from the K-map, so let's go ahead and put it in there as well. And we're going to get 0, 0, 0, 0, 1, and then we put don't cares in the rest of the boxes because those states don't ever happen. And so we end up getting, this is again for the stop output, stop equals S2, just as we surmised just by looking at the truth table. So now we can build these equations using using circuits. And so, in general, just like all of them, we'll have a state register. In this case, we'll have 3 bits of state, S2, S1, S0. We'd pull those state bits around and then bring in our inputs, mode, start, finish, and pause. And then we'd basically just pull off what we need to build that next state logic to create the next state. So we'd pull off what we need from the inputs and the current state. And then we'd build our output logic. I'll show the output logic because it'll take me, be pretty quick. So done equals S1 and S0. Here's our output logic. Done, and stop is just equal to S2. And we'll put in our gates for our next state logic here.